So we're finally starting to get into calculus proper with the topic of limits. The first thing to know about limits is that they're really not that scary. It's a little bit of an abstract topic, but it gets pretty computational pretty fast. More importantly, limits really are a vital foundation for the rest of our course. Everything we do in calculus is going to be some kind of limit or other. And limits turn out to be a really important human achievement, along the lines of spaceflight, the Mona Lisa, things like that. I look at the limit concept as a real victory for humankind. You should know that a lot of the stuff we're learning in this class is pretty old. It was developed in the 1600s and 1700s, but limits, the notion of limits as we're going to treat them, it was quite a bit more recent. That came around the turn of the last century, so the early 1900s, late 1800s. So the rough idea of what a limit is this. And you're looking at an input value or something like an input value a. And what we're going to do is take input values x that are close to a, and we're going to figure out, well, okay, as we move that x closer and closer to a, the question is, what happens to f? In this picture, you can see what's happening on the graph up here. And then the values, of course, are represented on the y-axis in this case. So the question is, as x goes closer and closer to a, what is f of x doing? In this case, it looks like the values of f, these points along the graph, are trending toward that point there, which means that the values of f are going toward some value over here, and we call that L. So that's a visual representation of what it means for the limit of f as x go to a to equal L. So in mathematics, rough ideas usually aren't enough to actually get the job done. We need a formal definition. So our formal definition is going to look like this. Now that's a lot of words, and really a mathematical definition, if it's going to be a formal mathematical definition, should probably involve a few more symbols. But it turns out this wordy definition has all the information we really need. The idea is this. You tell me how close I need to be to L. That is, you tell me the tolerance that you require of me. And the limit of f as x goes to a equals L means that no matter which tolerance you give me, no matter how small, it might have to be within 1%, within 0.01%, within a micron, whatever it is, then I can arrange that. As long as I'm able to make x very, very close to a. So the closeness of x to a that's required when you do that, that's called the precision. So you can think of this as a contract. You tell me the tolerance, and I say, okay, whatever the tolerance is, I'll figure out on my end what the precision has to be in order to guarantee that particular tolerance. What does this look like in symbols? We're going to represent that required tolerance by the number epsilon. So we say no matter what that number is, no matter how small epsilon is, it should be positive, because tolerances are positive. In fact, there is a precision delta. Delta will be our precision, so that we can ensure that f and L are close to each other. What does it mean for two numbers to be close? It means their difference is small. That is less than epsilon, simply by making x minus a in absolute value less than delta. That's saying x is close to a. X and a are both numbers. So to be close means their difference is small. There's one more thing to add here, which is that we don't care what happens when x equals a. We just don't care. The idea is we care what happens nearby to a, and by nearby we mean as close as we could possibly get, but we really don't care what happens at a itself. There are two other versions of the limit concept that we're going to talk about. The first is the handed limit. Handed limits come up when you only care about values of x that are less than, or only care about values of x that are greater than, the number a that you're taking the limit at. If we're interested in the behavior of f when x moves up to a, that is to say moves towards a from the left, we call that the left-handed limit, and the notation for that is the limit as x goes to a, and there's a superscript minus sign on that a. Now you might get confused because it looks like we're moving towards the right, which is in the positive direction, but just remember we're interested in the values of x that are less than a, so they are to the left. We're moving from the left to the right. On the other hand, if we care about what happens to f as x moves down to a, or moves toward a from the right and is moving in the leftward direction, we call that the right-handed limit. That's written as the limit as x goes to a with a plus in the subscript on top of the a. So notationally, the difference between these is just there's a minus sign or a plus sign down there on the a, and you should be really careful to pay attention to look out for those because they can be really small and you can miss them. Limits at infinity may sound really cool and maybe a little bit intimidatingly philosophical, but all you have to remember is that at infinity just means what happens when the input is increasing without bound. So as you slide your input value to the right as far as you can go, you just keep going and going and going and going. Of course, you never get there. That's what infinity is. Maybe your function f is doing something. That description of what f is doing, that's the limit as x goes to infinity of f. We can also ask the question, what happens as x decreases without bound? That is, as x goes all the way to the left and just keeps going to the left. That's called the limit as x goes to minus infinity of f of x.